So we're doing model selection, aka decision theory in some sense. We'll have to talk about properties of decision theory, aka hypothesis testing in some sense. So all these things kind of overlap each other. We have to understand all of that. Hypothesis testing is really just choosing between two things. And so if you can choose between two things, you can choose between three things too. So all of this can be extended to selecting something out of a collection. Which one do you think is most reasonable? Now what that means different things to different people. And so a lot of times when we're arguing over procedures, what we're really arguing over is objectives. And so we have to understand what the various objectives are. I just want to take you through some of the mechanics today. And we're not going to leave this discussion for at least a week and a half. So I'm going to be answering all these questions, which prior, how do you do this problem, all of these issues, and then what are the repercussions? What are your choices? What do they actually mean in terms of your analysis? So we've done everything a little bit intuitively, and we'll start there, and then we'll build it up. So just remember the basic setup is I've got some theta in some collection of values of thetas. So here's a collection of thetas right here. I'm going to call this model class H naught, the null. And this would be some other collection of thetas. So is theta in this range or is theta in this range? And there's a lot of different ways you can set this up. So maybe this is a point and maybe this is an interval. Maybe these are both intervals that don't overlap each other. Maybe these are two different points that I want to compare to each other, but they're two different collections and they do not overlap each other. So I'll call this model class H1. Some people will call that H alpha or something like that, or HA for the alternative. And the typical nomenclature is that this is the null hypothesis and this is the alternative hypothesis. But basically I'm just trying to say where I think ranges of thetas are. And I want to make a decision. This can be contrasted to just doing inference in the first place, where it's like in inference we're doing something different. It's a little bit different of a mindset. I just tell you where I think thetas are. And so in a lot of contexts, I just prefer to do that. I just tell you where I think thetas are. And so in that guide, I'm also saying where I think they're not. And we're quantifying that. And I kind of like that. In very high dimensional settings, when you're trying to make a decision between a lot of things going on, it becomes overwhelming to do that and tell everybody, here's where all these different things are, and how do you think about it all. And so we're very tempted to just make choices right here. I used to believe that people want probabilities and they want collections of things and probability statements about all that, but I guess I'm wrong. I think what humans want is us to make decisions for them sometimes. Just tell me what to do. And that, I think, is where a lot of this comes from. Is just, I don't want to hear about all that. I don't want to put thought into things. I want you to make a choice for me. And so when a scientist or an engineer or somebody comes to you and says, I want you to make a choice for me, you need to understand the repercussions of all of those decisions that you're going to be making. And so what does it mean to make these various choices? And so I spend a lot of time deliberating with people and explaining to them what the different things mean. And I try to understand it in the context of their problem. So I think a lot of people have tried to automate this, and I think that's a mistake because there's ramifications. So we'll be understanding those. Any questions about the basic setup? Two different collections of thetas such that they don't overlap each other. We want to decide, aka model selection, decision theory, hypothesis testing. Riddled with controversy depending on the hypotheses we're going to compare. I want to just point out a very typical setup is H naught theta is equal to a value, something, this is just a point, compared to H1 theta is a collection from some interval. So I'll just write it like this. Not equal to theta naught. It's everything else. Okay. So that's a pretty typical setup that people will study. This is a really bizarre comparison in the first place. This is one point, and this is everything but that point. So if somebody actually walked in, and this wasn't done on a computer, and it wasn't a simulation study, and they said to me, what do you think? You think theta's one point, and we're thinking about maybe a continuum? Or do you think it's this? Every single time I'll just say that. So, and I'm not being facetious, it's probably in there. So the question is a little bit more involved. Is this reasonable? Can I take this as an answer, and is that a good answer? And so they're not asking this specific question, is it theta naught? They're saying, is it close? And what we're really arguing about is what close means and the ramifications of what close means. Okay, so this is a strange setup. So this has like infinitely more support than that, just because of the size of everything. So one thing to just kind of understand up front is the cardinality of that. How big is this set? It's just a point. And the cardinality of this is way bigger. It's so much bigger that we can't even make the comparison. And so when we say something has measure 0, what we mean is not that the probability of it occurring is 0, it's that what I'm comparing it to seems so unlikely and it's so vacuously small that we call that a 0. So that's a different thing altogether. Okay, this is the contentious problem, and you can kind of see already just by the what do you even mean by this, that this is going to have some issues. That the comparison between a point in a whole interval, or potentially not even just an interval, but something between negative infinity and infinity, that's a bizarre comparison. And this is probably the comparison most people are making all through science. So no surprise that people are having a hard time with this. 100 years after this was kind of introduced, we're starting to think about it a little bit more. What does this mean? Should we even be doing this? My basic thought is, if it's just one parameter that you're thinking about, just estimate. Don't even deal with this question. Okay. But then we have to contend with the rest of the scientific community. And they say, no, we want to actually answer that because it's been done so many times. Okay, so what Bayesians do, and this is always true, this is a generalization, and you can apply this however, but there's lots of issues with this equation, is what a Bayesian's going to do is probably compute something like the Bayes factor. And this will be the basis for their comparisons. So if this thing, BF, is greater than 1, it supports the null. I'll just say it like this. The null, I'll say H naught, has more support. From the data. That's X. Okay, so you're imagining that there's some sampling model that I've collected my data and I'm writing it down like this. If it's less than 1, it supports the alternative. And so what are we doing right here? We're really just averaging. So, and think about the prior as just a weighting to different thetas. How much weight a priori do I want to put on those various thetas? So if I were testing something like at a point theta naught, do I want to put just as much weight on things that are close to theta naught in the alternative as I would very, very far away? And probably not. If you're testing theta naught, you want to probably put more weight on values that are close to theta naught. So if theta naught, for instance, was 0, I probably don't want to put a ton of weight on values that are greater than 1 trillion or 1 billion. Why am I testing theta naught in the first place if I thought that competitive values were trillions of units away? So we probably don't want to place the same amount of mass on everything everywhere. It depends on the hypothesis at hand, of course. We'll be grappling with that. But these are really just weights of how we're going to weight things. Before I wrote it like this, where I wrote the likelihood. given x. And it's the same thing. We're used to doing this interchange. So I take my sampling model, I'm treating it as a function over theta. I'm really operating on the likelihood function. But oftentimes you'll see people write this. This is the same equation up to proportionality, but it appears in both the numerator and the denominator, so any arbitrary constants cancel. And so I'm just plugging the likelihood function in right there. But I'm writing it out like this, just to change things up a little bit. And so what is this thing? I'm going to also add just a little bit more notation to this, although I won't do this all the way through. This is kind of a dummy argument, and it's kind of implied, is I'm only operating on the likelihood when I integrate over it over theta naught, this range of theta naught, so this whole collection, this whole space, not just one point in this case. It could be one point, whatever this collection is. I'm only integrating and throwing in values into this equation that live in this space, because that's where I'm integrating in that. And this prior is placing mass just on values in theta naught, right here. And so, and that's being implied by this notation right here. So I'm just going to add a little bit of notation. Just write down that this is the function, the values of theta that are in this model class H naught. And I'll do the same thing right here. And I'll just provide us a little bit of notation so we can understand this a little bit better. So this is an averaging, where I'm averaging over this weight. I'm taking a likelihood function, I'm averaging it over that weight that lives in a different space than this right here. So this is a comparison of averages. So this thing right here is just this. Fx given H naught divided by Fx given H1. And this is really just the margin of the data. So this is the marginal distribution of data. So that's the margin of the data under H naught. And this right here, something similar. This is the margin of the data under the alternative. So I'm averaging over everything. So I'm averaging over my model class. So I'm averaging every competitive value, and I'm telling you how to put weight on it. And I'm just averaging, so the Bayes factor is a comparison of averages in the model class. And of course, how you weight your answer is going to make a difference. We have to understand what difference it makes, what are the repercussions, and how do we want to average. So, but I think it's at least reasonable to think about this at an intuitive level. It kind of makes sense. We wrote down last time the maximum likelihood ratio test statistic. We'll write it down again. So the max likelihood ratio test stat looks like this. I'm going to take a maximum over theta in my model class H naught, and I'll write it down as the likelihood function. For arbitrary reasons, all the normalizing constants should cancel in this. This is going to be the max over my other model class likelihood theta given x. And if you wanted to take this thing and plug in f of x given theta or something proportional to it, these are equivalent. So again, nothing's changing. And so my interpretation of these two equations are very similar. This is how well the data supports each model class in both cases. But the operator is different. So this is an on average sense of comparison, where this is taking my best candidate values and making the comparison. So I have two different model classes, H naught and H1. And the question is how should we compare them? That's the first question. Do I want to average over every competitive value in these two different model classes? Or do I want to compare just the best models in those two different model classes? That's a reasonable question. I'm not sure that that's necessarily for a statistician to decide how you make that comparison. So do I average over all this stuff in those different models and make the comparison that way? Or do I look at my best competitive model and I make that comparison? And I've gone around to lots of scientists. I used to do this in the early part of my career, and I would try to explain this to them without going into any nuanced mathematics and say, what is it that you want to explain as a scientist? And I think most of them will come back and say, well, I want to just compare the best to the best. And they're different things. And then I have to explain to them what the ramifications of doing that are. So I think intuitively, sometimes this one makes a little bit more sense than just comparing things on average. But they both have some intuitive appeal. So let's try to keep building this up a little bit. But there is a connection between these two things. Sometimes this integral right here is hard to do, and you'll see people take this thing and use it as a bound on the Bayes factor. And we'll be going into that later. So this does bound the Bayes factor. So there is a bounding equation that we can study. In next week, we'll see some examples where we study that. Okay. Let me tell you a connection between posterior probabilities for hypotheses. So this is true. Here's a fact. And here's a couple facts. So before I tell you about posterior probabilities on nulls and how Bayes factors relate to them, I'm going to write down the Bayes factor has this other interpretation. This is going to be the probability of the null hypothesis, the posterior probability, divided by the posterior probability on the alternative, given x, divided by the probability of h naught, divided by the probability of h1. These are equivalent to each other. So I just want you to see where this comes from. I wrote it out this way where it's just the marginal. There's no thetas in this equation. There's no thetas in that equation. They're removed through averaging, where I've averaged over this prior, right here. This is pretty obvious. And so what is this thing? This looks like f of x given h naught times my prior. Let me give this some notation. I'm going to call this pi naught. And I'm going to call this pi 1. Where this thing right here is going to be 1 minus pi naught. They're complements of each other. This is the prior mass on h naught. And this is going to be the prior on h1. So we haven't talked about that prior yet. So there's 2 layers of priors that go into a Bayesian hypothesis test. There's the prior, the weighting on theta itself, and then there's how much I want to weight those hypotheses. So maybe a priori I have some belief about the 2 different hypotheses themselves. So there's 2 different priors. There's the prior, how we place mass over the parameter space, and then there's how much weight I want to put on those 2 different hypotheses. This is very easy to think about, right here. So if I didn't want to add a lot of bias to one of the hypotheses, I might be inclined just to pick this to be 1/2. And that 1/2. I put equal mass on both of them. And so it kind of just washes out, and the Bayes factor is the ratio of the posterior hypothesis, posterior probabilities. So this right here just looks like this. Pi naught divided by fx given h1, pi 1 right here divided by pi naught over pi 1. So the same things happen. So these pi naughts cancel, pi 1s cancel, and we're back to this. So this is just Bayes' theorem sitting right here. So the Bayes factor is not the posterior ratio, but it's the posterior ratio compared to the prior ratio. And so I like thinking about the Bayes factor like this, that it's a marginal of support of the data, but I can understand the appeal of thinking about this thing right here, where I'm just looking at the posterior odds divided by the prior odds. So it means after I see the data, how did my odds change? And that's what the Bayes factors interpretation can be. It is that. Let me just say that. So this is going to be the posterior odds divided by the prior odds. Again, when I use the word prior, I mean the prior on the hypothesis itself. So this is a discrete thing where the parameter itself is continuous. And you might think, why do I want to put a lot of weight on one hypothesis over the other? I thought I was comparing, I didn't know that. Very often, you'll use uniform probabilities on these things. Saying that, if I was comparing two different models with more parameters in it versus less parameters in it, so if I had a regression model with 1,000 parameters in it versus a regression model with very few parameters, maybe 5 parameters in it, I might want to adjust how I'm thinking about this. And it's a mechanism for adding a penalty. So I might want to penalize harder models with more complexity. So at least it gives us a knob where we can add that penalty in there. I will point out that it's automated through this as well. That there is that penalty factor that shows up here. If there's more parameters down here than there are here, you'll notice that I have this. If I were thinking about those priors as independent, I would have a producting over something that probably lived between 0 and 1, and it would regulate that space. We need to see examples to really understand that. But what I'm telling you is that there's knobs that you can play around with. If I didn't know anything about the models and they had similar complexity, I'd pick them to be equally likely. This is where most people jump in and they'll start asking about this. They're really interested because it's easy to understand. How did you weight everything? And usually the Bayesian gets out really easily out of the audience's question and say, I just picked them to be 1/2, 1/2 because I'm objective. What they should be asking about is this one, in that one. And very typically they should be asking about this. And we'll have to see this through some examples, what the influence and impact is. So that's one way to write down the Bayes factor. I just want to write down our prior, our overall prior on theta, my entire space where this thing is going to be equal to the union of my two spaces. So our overall prior on everything, this equation is partitioning how we're splitting up the space, but it's going to look like this. Pi theta is going to be equal to pi naught pi h naught theta, that's this, plus pi 1 times pi h1 theta. So it's just an averaging over these two things. So if I wanted to think about this, instead of writing it out like this, I could maybe write down pi naught, just like to always think about having the right notation. This is going to be theta given h naught. So that's how I'm thinking about this. Plus pi 1 pi theta given h1. So this is just notation telling us how we're constraining the model, how we're constraining those two different spaces. So this is probability of h naught pi theta given h naught plus probability of h1 times my continuous prior on theta. So this is how these priors relate to each other. And so again, this is just Bayes' theorem where I'm just averaging over the hypotheses. I only have two hypotheses that I'm comparing in this context. If we had more, this would be a bigger equation. For your problem on the homework, you've got 4 hypotheses that you're comparing. So there's going to be 4 terms in there, and you're going to add weight to each one of the terms. You probably add 1/4 weight to everything in there. And we'll have to talk about what those pi thetas are. I choose them to be delta functions. There's really no choice. That's just a prelude into the homework. But this just looks like marginalization. So I've marginalized out my hypothesis space, and I come up with my total prior on this. If this is going to be proper, these have to be proper as well, and they have to integrate to 1. And so if I'm going to make this comparison, we're going to need this to be true. So I'll just make a big note. So this is huge. Pay attention. Don't forget this. So we'll need integral pi h naught theta d theta to be equal to 1 and pi h1 theta d theta is equal to 1. Where I'm going to be integrating over my null space. So I'm going to change my notation just because I'm running out of room. So that's just the same thetas are in that cap theta h naught. So I'm just going to change my notation right here. If let me write it down like this. Let me say in most cases. And I'll just spend some time explaining what I mean by this. So in most cases, you're going to need these to be proper priors. There are contexts where you can have improper priors. This is where we get a whole wrench in everything. So let's just look at an example or two. So here's an example. Let's just say we're going to consider some model. I'll try to make it look a little bit more complicated than just testing something that's normally distributed. I'll add some covariance. So that's where I want to go with this. Example, yi's are going to come from some model, some linear model. dxi's plus some error. Where this error, I'll let this be normally distributed. So very basic setup. Simple linear regression. And possibly, I have a hypothesis like this. Alpha is equal to 0 versus alpha is not 0. Okay, so this is that sharp test that is contentious. So I want to just point out the first thing about this. So this is sharp testing. And this is probably where we'll use this setup, but we need to understand all the repercussions for dealing with things where I've got a lot of betas. And we're going to decide which betas are in there. I usually don't test the intercept in most problems. I just say, let there be the intercept. Always have an intercept in there. So even if it's close to 0, just stick it. You know, probably a good principle. If you don't include your intercepts in a lot of cases, you're going to foul everything. Okay. So the question is how might we pick our priors? So which priors? So maybe pi naught and pi 1, maybe that's easy. So if I didn't know anything about these two different, this hypothesis, maybe that's an easy thing to pick. So in some sense, this is objective. We'll understand that better later. But my priors for the other parameters, we need to put a little bit more thought into. So I'm just going to write down h naught. This is a prior on alpha. This is going to be a prior on the alternative. And I'm also going to need some priors on my beta. Okay, so I have a lot of things going on here just to distinguish when we need to use proper priors or improper priors. So in most cases, so and I'll just put an asterisk when parameter does not appear in both models. I'm embarrassed for a lot of people because in the early days of Bayes, people were violating this rule and coming up with just total trash answers. That's okay, things get fixed out, please.
Oh, sorry, what was the difference between pi naught and pi h naught of alpha?
So my pi of h naught of alpha is playing the role of this right here, where my pi naught is the weight on the hypothesis itself. So one of these things is weighting alpha that lives in this continuum, and one of these things is just how much mass I'm placing on that, on those hypotheses themselves. So we have this same prior that we just tried to think about. So we have pi naught times pi alpha given h naught. Or I'll write it down like this, h naught plus pi h1 times pi alpha h1. So there's these two layers. So how much mass am I putting on this? How much mass am I putting on this? And this is telling me how to smear the mass over the space. Patrick.
So then pi of h naught would be pi naught times pi of alpha given h naught.
Pi of h naught.
So pi of h naught alpha is your prior on your h naught
this
times
one.
your.
This one, right? Yeah,
Yeah.
absolutely. This is just to distinguish the notation. This is that.
Okay.
So,
Well, yeah.
it's a little bit of leap. I'm just changing the theta to alpha. So the question is how do I place these priors? Let's start with this one. Which prior would you choose? Just in general, based off of everything that you know already. Sure. I wouldn't pick Wishart. So, for all kinds of reasons. One, it's one-dimensional. Two, alpha can live anywhere. So in the typical regression setup, we might take this thing to live between minus infinity to infinity, and same with this, minus infinity to infinity. Usually those are unconstrained. If there was a constraint in there, the problem becomes a little bit harder, but we could solve this one. So maybe normal. So I need to center this somewhere, and I need to come up with some variance for the beta. And you'll have to choose those parameters to do this. And there'll be some ramifications depending on how you want to weight things over that space. That if I centered this very far from where the true answer was, and I let this be very small, I'll probably be adding some sort of a constraint to the model that I really didn't want to do. So we have to be judicious about this. So maybe this. How would you pick this? That's the one I'm always thinking about. I think about variances way more than I think about means. What's that? You'd pick that to be gamma? So you'd make it Cauchy. So what Jennifer said is pick maybe this to be on the inverse scale, a gamma half-half or something like that. And inadvertently, all she did is say, I don't actually like it being normal. I want it to be t-distributed or Cauchy or something like that. So you're changing the model. That's fine. A lot of people do that, and I oftentimes do that. But since we already decided normal, let's leave the wrench out of it for a second. So how might you pick that? So if you're just doing estimation and you try to estimate beta,
Make it infinite?
Make it infinite. So inadvertently you would, or maybe very intentionally, you'd be driving this to a flat prior. That is okay in this case. And I'll point out why. It doesn't adhere to this. right here. We need to be more careful for these right here. So in some sense, in my null model, right here, alpha is not appearing. I'm just like taking it out. So by saying alpha is 0, I'm removing it from the equation. So this is a case where the parameter doesn't appear in both the null and the alternative. Or it does in some sort of weird sense, but if I removed it, it would be equivalent to placing infinite mass on 0. So let's just think about this. What prior right here would you pick? There really is only one way to do it. Flat. Point. Those are very different things, but maybe that's what you meant. Maybe you mean uniformly distributed on the point, and maybe that's what flat means, which is the sharpest thing I can think of, which is the least flat thing, but I get it. But there's only one way to do this, and that's just delta function is alpha is equal to 0, right here. So if I integrate over my delta function, it'll put all the mass just on one point, right here. So this is a delta function. So this is going to be 1 if alpha is equal to 0, 0 otherwise. So that's the same old thing. So when I integrate over this thing, it's just that 1 that shows up. So when I end up doing this right here, delta function alpha is equal to 0, d alpha between negative infinity and infinity. This thing is the easiest integral in the world to do because it's 0 everywhere and 1 somewhere. And so it's 1 only at one point, and I add continuously all those other zeros. This thing is 1. So this is a proper prior right here. Here's the big question, and this is why I say I'm always interested in the alternative prior. Which prior do we use here? You're not supposed to know the answer, but you're supposed to guess. Okay.
I don't want to say flat again.
Yeah, probably not. So because it does violate this. So we already know that's probably not a good idea. We have to understand why. Peter.
Do you try like a double exponential with a hole in the middle of it?
A double exponential, so I'll end up, he means this sort of thing. And so when I end up taking that point out right there, I'd probably ask you, why do you like the double exponential and all of that? Certainly would make the integrations really hard to perform, but I guess you could. So that's probably an okay answer. Some people will mix over this and do all kinds of funny things, and they end up creating what's called a Bayesian lasso. So you're one step away from something that's really a good idea. We'll talk about that later. Interesting choice. Other people. What do you think? So let's just entertain what happens if we do pick a flat prior. So let's just look at our base factor equation and think about a flat prior. So if we used pi h1 alpha is going to be proportional to 1, aka flat, everything goes wrong for us, and we can see that. So this thing right here is going to be the integral. Over my normal model, I'll just still write it down as fx. We could parameterize this if we wanted to. And this is going to have my alpha in here. It's going to have my beta in here. We won't touch beta quite yet. Well, I guess we can. We already wrote down beta. And we've got our, this is going to be my y's given my x's. Is how I write that down. Same thing over here. Integral fy alpha, beta, and x. Now I need to start including my priors. So this is going to be pi alpha on h naught. This is going to be pi h1 alpha. And then I'm going to have pi beta. pi beta appears the same way. I'm not testing beta. That's not part of my equation. Right here, this is going to be d alpha, d beta, d alpha, d beta. And this is going to be alpha is an element of h naught. Beta is going to be an element of minus infinity to infinity. So my integral sign is a double integral. Okay, where I'm telling you both things of support. The reason I do this and always use one integral sign is because I work on problems that have a lot of parameters, and I don't like to just draw the integral sign 10,000 times. So this is going to be alpha is an element of the alternative, and this is going to be a beta is going to be an element of the same thing, minus infinity to infinity. If you want to see what that equation is, you're going to be using this in the future, like Fy given alpha and beta and x, this is going to look like this. Here's at least, well, I'll do it the easy way. I goes from 1 to n, so we're going to assume we have n data points. Not sure I wrote that down, but I meant to. So this will look like 1 over root 2 pi. There's a sigma in here. We don't need this. I'm going to assume you know sigma. If you don't know sigma, you'll place a prior on it. And it appears in both models. E to the minus 1/2 yi minus alpha plus beta xi squared over sigma squared. So that's what this thing looks like. That's what we'd be plugging in there. Later on, we'll actually do the integrations. Patrick?
Question back on the delta. Isn't it that the delta evaluates to infinity, but the integral evaluates to 1?
Yeah, you're right. So the density function is jumping off to infinity. It'd be the correct way to do this, but I always just make it 1 and everything works out. But if we were in a measure theory class, your math professor would agree with you and not me. So just leave it the way that it is. Though. Just put it a 1 or a 0. Everything works out great. The density, what is the density? It's infinitely high. And it has no width. And so as I take those limits, it's done in a way so that when we do integrate over it, it integrates to 1. There's been a lot of discussion about that back in the 60s. Whether or not that's a valid thing to do, it is. I think we're permissed. So, but I'm going to still leave it just like this. It makes everything easy. But if I were in a measure theory class, I would take your advice. Okay, so let's just think about this. What would happen right here? If we did use this flat, well, this thing's easy right here because I just have this delta function. So delta function, alpha is equal to 0. It's going to show up. So this is going to be a switch that turns to 1 in only one value. So this is a very easy integral to do, and I'm just going to be plugging alpha is equal to 0 into this equation and doing the rest of my integration on beta right here. If we think about beta right here, maybe we pick some normal, but somebody said maybe turn this into an infinity, and that's going to say that this is going to converge to something that's flat. Beta appears in both the numerator and the denominator. So if I did pick this to be 1, we have a nice cancellation between those parameters. If I pick this to be 1, it feels like I didn't do anything wrong. But let's just see if I change some of my arbitrary conventions. Let's say instead of picking this to be 1, I picked everything to be proportional to 10. It's the same thing. It's that same shape. And let's say I pick this to be proportional to 10, right here. Let's see what happens. If I pick my 10s on the betas, they still cancel each other. But if I pick a 10 right here, I just made a Bayes factor that's 10 times smaller than the other one. So what I mean, this is the important thing, is if you have a parameter that appears in both parts of the model and everything cancels, then no problem on using it. If you have some arbitrary convention on something and it does not cancel out the equation, you cannot use it. So this is the big sticking point. And some people don't understand this very well. In estimation, it's very common to use improper priors. But using improper priors on parameters that you're testing is not valid. You cannot do that. So Sering asked me an interesting question. Can you use a Jeffreys prior on a hypothesis testing problem? It depends. If that parameter is appearing in both models, and I'm treating it the same, then yeah, no problem. If you're using it on a parameter that only appears in one of the models, then you have to be careful. If that Jeffreys prior is improper, then no. If it's proper, then yes. Some Jeffreys priors are proper. So Bernoulli is a good example. The beta half-half thing. So you would end up having to include the normalizing constant, though. I will point out on these, you always have to include the normalizing constants if they don't cancel. So just remember this. If you're testing a parameter that does not appear in both models, you cannot use improper priors. You need them to integrate, and they need to include the normalizing constants, because those things won't cancel. If you're ever confused about it, just write down the equation, fiddle around your arbitrary decisions. If it changes your equation, you just make a huge error. So, does that make sense? Okay, that's probably the biggest thing I want you to think about. Now that, of course, brings up, okay, so I can't do this. That's forbidden. Oh, sorry, not on this one. This one being flat is forbidden. So you can't do that. So maybe you might think, maybe I'll pick the normal prior because it's conjugate, and at least I can work through the integral, but I'm stuck with two questions. Where do I center, and how much variance? So you've got an answer, right? Where would you center? Yeah, probably at 0, probably where the null hypothesis is. Now, Peter says, you can't center it on the point because they don't overlap, but it's a continuum, so I could remove that point arbitrarily from the space. Or I could leave it in and it has no impact. So it has measure 0. So you probably center it in theta naught because that's what you're testing, and then the whole question is what is the variance? And that's the big part. I need to walk you through a bunch of equations and show you how the variance impacts your answer. But if you did do that and you centered it at theta naught, and you took your variance out to infinity, you would end up cutting infinite mass on the null. You don't want to do that. So the variance parameter for what you're testing is really saying, so if you did this, and we need a lot of conversation here. I hate that I'm going to leave you right in the middle of this conversation, but we might take this to be 0, and this to be some variance, and this is the key. What the interpretation of this is how far from the null do you need to be before you're willing to reject? So it's really calibrating an effect size for you. And so the Bayesian is going to force you to answer this question. How far from the null do you need to be before you're willing to reject it in this probabilistic sense? And that kind of makes sense. So the Bayesian is going to be doing this comparison on average, but they're also going to be calibrating how far from the null you need to be. And that's the part that people don't like about Bayesian hypothesis testing, is you have to confront that question. And people, they just throw it under the rug. I don't like their analyses. Now, one easy thing that people will do is they will standardize all of their data, and then they'll say, I don't know, I'll just pick it to be 1. And so they're calibrating it in the sense that it's so many standard errors away. We'll talk about that next week. I'm going to leave you with this last equation, and we'll pick up with this next time. Let's see if you can prove this. You can prove this from either definition of Bayes factor that I gave you, but the posterior probability of the null hypothesis, given all of your data, so I'll just go back to using X. If you're a regression problem, I'd have Y's and X's in here. But this thing is this, 1 plus the Bayes factor inverted times 1 minus pi naught over pi naught. So this is my probability of my null. This right here is the probability of the alternative. They're complementary. They live in different spaces. Inverted. And so we'll write this down next time, but this is Bayes' theorem in disguise. This looks just like this if you work it all out. This is going to be f of x given h naught pi naught over f of x given h naught pi naught plus f of x given h1, this thing right here, which that's just 1 minus pi naught. See if you can do that over the weekend. Just unravel this thing, write down the definition of the Bayes factor, and you'll see that this equation is that equation, and this is obviously that. This is just Bayes' theorem applied to the hypothesis. Where did theta go? It got integrated out. And so the Bayesian is always forcing you to integrate that thing out. I will point out, just as a final thing, the probability of H1 is going to be equal to 1 minus the probability of H naught, given the data. They're always complementary. So the Bayesian, when they report to you, they're always giving you a comparative answer, that this is always baselined in the alternative. They all add up to 1. And this is the answer to Danielle's question from last time. Can you explain why at a point all of those posterior trajectories will add to 1? It's because we're placing a probability on that, and we adhere to the rules of probability. Of course, we have to adhere to how we place mass over the alternative, so we know how everything is weighted compared to each other. Let's come back next time. This is going to take us quite a few days to kind of work through, see examples, understand what the impacts are, but we'll apply it soon. So that's all I have for you. Have a great weekend, and I'll see you on Monday.